Welcome to an introduction to Verilog. In this video, you will learn the history of the Verilog HDL language, an approach to learning Verilog, and a first phrase design example done 3 different ways showing the versatility of Verilog. Verilog, which was standardized as IEEE 1364, is a hardware description language used to model electronic systems. It is most commonly used in the design and verification of digital circuits at the register transfer level of abstraction. In Verilog, a design consists of modules. In addition, most designs import library modules. A simple AND gate in Verilog would look something like the following. So here we see an initial couple lines of comments. Verilog code lines that begin with a pair of slashes or comments and do not generate any hardware. This is a module that describes a simple 2-input NAND gate. The module name is AND gate, which is followed by a sensitivity list with inputs x1 and x2. The output is F. The assignment statement assign F equals x1 and x2 will cause the synthesizer to create an AND gate in the FPGA. The ampersand indicates that the signals are to be ANDed in a Boolean manner. All modules end with an end module statement. So Verilog is an acronym for verifying logic. Verilog is a modeling language created by Gateway Automation in 1984. Gateway is acquired by Cadence in 1990. With the increasing success of VHDL at the time, Cadence decided to make the language available for open standardization. Cadence transferred Verilog into the public domain under the Open Verilog International Organization, now known as Accelera. Verilog was later submitted to IEEE and became the IEEE standard 1364 in 1995, commonly referred to as Verilog 95. Extensions to Verilog 95 were submitted back to IEEE to cover the deficiencies that users had found in the original Verilog standard. These extensions became IEEE standard 1364-2001, known as Verilog 2001. Another update occurred in 2005. In many cases, the FPGA vendors are supporting Verilog 2001, may not support 2005 as of yet. And so it's important to kind of know the distinction between these because it may affect how the synthesizer treats your Verilog code. As of 2009, the System Verilog and Verilog language standards were merged into System Verilog 2009, which is now IEEE standard 1800-2009. Current version is IEEE standard 1800-2017. While some FPGA vendors' tools support synthesis from System Verilog, most of them, in fact all of them, will support Verilog, but only some will support System Verilog at this point. And the version of System Verilog they support is probably a couple of revisions back. It might be still 2009. That's something that you have to check with your FPGA vendor tools as you're working with Verilog as an HDL input. So how can you learn Verilog? It's like any other language. If you were going to learn, say, Spanish, you would first learn a couple of key phrases, and you'll practice them and practice them. So you learn things like, where's the bathroom? How much for a beer? You know, important things that you need to know in order to get around wherever you were and communicate with people in Spanish. In Verilog, you also learn a few key phrases. And then after a while, you have a sense of how the language works. And then the next step is to learn the grammar and the syntax so that you can put larger concepts together. You can make compound sentences and things. And you do a similar thing with Verilog. You'll learn how to make smaller constructs and then bigger constructs as you go. And then, of course, you just want to practice, practice, practice until the point comes where your knowledge of the language is become intuitive. And you don't even really have to think about it in order to write Verilog code. So this is an example of a first phrase. It's a 4-bit comparator. Here what you see is a number of gates that have been combined together. The idea here is that we're going to compare two 4-bit vectors, A and B. And to do that, we're going to use these XNOR gates here. So this is an XOR gate followed by an inverter, which gives you an XNOR gate. The XNOR will be equal to 1 only if all the inputs are the same. So it's kind of like a 1-bit comparator, if you will. And then we're going to combine all 4 of these comparators together in an AND gate. If all of them are true, that means all the bits match up 1 to 1. Then the equals be true. So this is a typical comparator circuit. And so now we want to learn how do we write this, a description of this circuit in Verilog such that the synthesizer is going to create this exact circuitry. In general, there are 3 different ways to model circuits in Verilog. First is the structural modeling, in which models are constructed of gates, just as they would be in conventional digital circuit design, using predefined library modules for the gates. Second, we use data flow modeling at the register transfer level of abstraction, or RTL, using concurrent assignment statements. Third, we could use behavioral modeling, which uses procedural statements known as an always block, similar to process statements in VHDL. Let's apply each of these modeling styles to the comparator example and see what we get. So this is an example of a structural model of a comparator. It uses library modules for the gates inserted into the comparator module. The act of inserting the library modules is known as instantiation. Each instance of the gate model is wired to different signals. The first XNOR gate, labeled XNOR 0, has A0 and B0 as inputs, with N0 as the output. Each successive XNOR gate instance operates on successive bits of the input vector. The outputs of the XNOR gates are connected to the 4-input AND gate, which provides the output. This code will be synthesized exactly to the circuit of the comparator, just as we saw on the previous slide. This is the data flow model of the comparator. The data flow model provides an output as a function of the input vectors. The description of the comparator in this case is achieved in a single line of code, showing the efficiency of this modeling style. It's a lot less typing than structural model, but will synthesize to exactly the same circuit. The way to understand this statement is that vectors A and B are XNORed 1 bit at a time. The exponential caret symbol represents the XOR operation in Verilog, and the tilde represents an inverter. The 4 bits are then ANDed together as represented by the ampersand in front of the parenthetical expression there, and then that gets assigned to the output Y. In this particular example, we're using the 1995 syntax for the signal list that's part of the module. So you see the signals A, B, and Y are listed with a semicolon after the parentheses there. And then the inputs A and B are defined as 4-bit vectors, and then the output Y is defined. Next, we have the behavioral model. In the behavioral model, a special block of code known as the always block is used wherein statements are sequential and not concurrent as they are outside of an always block. In an always block statement, order matters. So here the output is initialized to 0. Whenever there is a change to A or B, the 2 vectors are compared, and if equal, the output is changed to a 1. Otherwise, it remains a 0. The synthesizer will again create exactly the same comparator circuit based on this description. Although a bit less efficient than the data flow model, this type of modeling can be extended easily to much more complex hardware. So this is the type of modeling that we'll tend to do the most once we become more experienced with Verilog. But the structural modeling and data flow modeling are still used in a lot of examples. So it's good to know how to do all three. So in summary, in this video you have learned a little bit about the history of the Verilog HDL language from inception in 1984 until the latest IEEE version revision in 2017. You've learned an approach to learning Verilog involving assimilation of vocabulary, phrases, and syntax. And you've learned a first phrase design example, a comparator, that's modeled by the use of either structure, data flow, or behavioral descriptions.